So what is the law of conservation of energy? And why is potential energy this, kinetic energy 1/2 mv squared, and work is force times delta x? So it would be very reasonable for us to say conservation of energy is a law, we just witness it all the time. In a situation where a rock falls from a hill and speeds up as it falls, that we could invent this thing called energy, where we represent it in terms of height in the beginning and speed at the end, and we find out that they're equal. And so we could say it's a law. What a law means, it's what you see all the time, you don't have to explain it, that's the way it is. You break the law of, like, speeding, you go to jail. You break this law, you get the Nobel Prize. Right? So this is a law because you can't break it. Now that being said, is there a theoretical basis by which we can show this? We've invented this thing called energy, and we say it's always conserved because we see it. Is there theoretical support why the kinetic energy should be 1/2 mv squared and not, let's say, 1/2 mv cubed or 1/3 mv squared? Why is it this value? This provides a theoretical support for this formula and this formula. And so if you can accept that we've invented this entity called energy that has to be conserved, and that work, which is force times distance, is equal to the change of energy, we can derive these two. And so we have something that's consistent. Let's say we start with a box that has no energy. E0 equals 0. And we put a force on it in this direction and move it some distance delta x. We can say that the work we did on the box is equal to the force I'm pushing times the displacement that I move in that direction. How does this give us a potential energy of mgh for gravity? Well, let's take a difference of potential energy, let's say from here to up here, where we have some height difference h. In order to change this energy, I have to put some work in, which is going to be force times distance. Now the force, if I put a force on it, I might accelerate it and some energy might turn to kinetic energy. Let's not let that happen. Let's push with just enough force to compensate for gravity so we move upward at a constant, very, very low velocity. So kinetic energy is essentially 0. And so this work turns to gravitational potential energy. Okay, so here is the rock, and there's the force of gravity pulling down. As I move it up, and I'm not accelerating it, if the acceleration is 0, the force of my hand must be equal to the force of gravity. So we can see that the force that I put on it is equal to the force of gravity times the height. And so this is just going to be mg times the height. So the work I do on this rock to change its potential energy is mg times h. So this one is no problem. Now, how about this one? I push on this box and there's no friction and I don't change the height, it just accelerates, and that work manifests itself as velocity, which we call kinetic energy. If we start with 0 energy, V0 is equal to 0, and we push on it, all of our work will be equal to the final kinetic energy it has if nothing is lost to potential energy or heat. So I can say then that the work I do, which is force times delta x, must be equal to the final kinetic energy. And so how do we express this? How do we express this work in terms of velocity? Let's see. We know force is equal to mass times acceleration. So what is acceleration? Acceleration is a change in velocity over change in time. And if the initial velocity is 0, that's just the same as the final velocity. So I can substitute this in, and now I have mv final over delta t times delta x. Now we need to substitute in for delta t. What's delta t? Oh, I can look at my velocity and my displacement. I can say, oh, I know that the average velocity is equal to the total distance I go divided by delta t. And so then delta t is equal to the total distance I go divided by the average velocity. Now the last substitution is important. How does the average velocity and the final velocity relate? And if we were to graph velocity versus time, it would be a straight line. We start at 0 because we're at rest. And here's my final velocity. And if the force is constant, then the acceleration must be constant. This is a straight line. So the average velocity must be equal to 1/2 the final velocity. And I can put this in. The average velocity is equal to 1/2 the final velocity. And so delta t is 2 delta x over final velocity. And I substitute this into delta t, and I have ½ mv squared. And so yes, if I start with a body that has no energy and I do some work on it, force times distance, the work that I do is equal to 1/2 mv squared. And that's a way to express the work in terms of velocity, which we call kinetic energy. So we were able to show that kinetic energy is 1/2 mv squared by simply taking the work energy theorem, that work is equal to the change of energy, and using our very simple kinematic equations that the average velocity is delta x over delta t, and acceleration is the rate of change of velocity.